Really coming out of this chapter, the two biggest things are polynomial equations, which is something like this, and being able to graph them and find the zeros. And then the last couple of questions are rational functions. So the ones that look like this here, being able to graph those with the vertical and horizontal asymptotes. So those are two big things coming out of this unit.
All right.
Okay. So question 1 is from 3.4 or 3.5, one of those two. Rational zero theorem. Here is the P divided by Q. That's the rational zeros theorem. Where remember P, factors of P come from that constant at the end. And Q is the leading coefficient, which is 1. So P divided by Q in this case is factors of 6 divided by 1, which is just going to be the factors of 6, so plus or minus 1, 2, 3, and 6.
Okay.
So that answers part A, determine all possible rational roots. Part B, factoring it means find the zeros. Factoring and finding zeros pretty much means the same thing. We need to write P of X in 3 factors like this. So what we need to do is figure out which one to start with from that list of possibles here. So I don't know, might as well start with 1. Now, the tricky part about this problem, and a lot of students fall into this, is noticing, or not noticing rather, that it goes from x cubed just to 7x, and there's no x squared term there.
Mm-hmm.
So when we're doing our synthetic division, we've got to put in a 0 for where that x squared was.
Okay.
So testing 1, see if it works.
Okay.
So what we get from that is one of the factors is x minus 1. And then the other factor comes from those coefficients right there, 1, 1, and negative 6. So we have x squared plus x minus 6.
Okay.
Now that we've gotten it down to a quadratic factor, the two choices you have now are either to try to factor it if it factors. If it doesn't, then you can use quadratic formula.
Okay.
But this one does factor. This is part B, we factor the polynomial. And the reason I want it in fully factored form like that is for part C now, because we need to graph. And in order to graph, we need to show the zeros or the x-intercepts, and that's what the factors tell us.
Mm-hmm.
So, and this is where it doesn't happen in this problem, but this is where you're going to want to remember things like multiplicity and whether the graph crosses or bounces at the x-intercept. So for example, if there was x minus 2 squared right here, then that 0 bounces off the x-axis, right?
Yeah.
So x minus 1 as a factor means that the 0 is x equals positive 1, and then x equals negative 3,
Okay.
and x equals positive 2.
Okay.
And since they all have multiplicity 1, those are all just going to bounce. To find the y-intercept, remember you let x equal 0. So if you plug in a 0 for all the x's, you can either plug it into the factored form, or you can go back to the original general form here, which I I would do if I was finding an X or a Y-intercept, because then all of these X's turn into 0, you're just left with 6 right here.
Okay.
So 0, 6. So that's our Y-intercept. And then it says end behavior.
Mm-hmm.
And that's determined by the degree.
Yeah.
So it's a third degree polynomial, which means the right side is going up and the left side is going down. So that would be our end behavior there. If it was an even end behavior, or if it was an even degree, like a fourth degree or a sixth degree, then the end behaviors are going into the same, both to infinity or to negative infinity.
Okay.
So then we just got to connect the two pieces of the graph, and there's a little bit of a span right here between these, between this X-intercept and this X-intercept. So if you remember when we had this unit test a few months ago, got to plot at least one more point somewhere here, like -2 or -1, because it may be that the graph goes way up here before it comes back down, right?
Yeah.
So let's plug in, let's plug in -2.
Okay.
I'm going to plug it into the factor form. So -2 minus 1 is -3. -2 plus 3 is 1. And then -2 minus 2 is -4. So -3 times 1 times -4 is 12. So it goes way up to 12 when x is -2. And since it's so far off the graph, you just kind of plot a point way up there.
Okay.
Call it -2, 12. The graph comes way up here, goes down through 0, 6. Now it crosses through both of those zeros because they have multiplicity 1. So the graph looks something like that.
All right.
So that would have been from section, well, a couple of different sections: 3.2, graphing polynomials; 3.4, finding zeros of polynomials.
Okay.
Question 2 is from the same couple of sections, graphing. The reason I put this one in here is because it has a leading coefficient of 6.
Mm-hmm.
So it just changes things a little bit, especially here for part A, the rational zero theorem. Because now Q is plus or minus 1, 2, 3, and 6. And then P is 1, plus or minus 1, 2, 5, and 10. So now the list of all possible rational roots is going to be all the factors of P divided by all the factors of Q.
Okay.
The way I do it is I start with one value of P, like plus or minus 1, and then divide that by all the factors of Q, and then move on to the next value of P. So we plus or minus 1 over plus or minus 1, which is plus or minus 1. Then we have 1 over 2, 1 over 3, and then 1 over 6. And then move on to the next factor of P, which is 2, and then do the same thing. 2 divided by 1 is 2. Now 2 divided by 2 is 1, and we already have that there, so you don't need to do that one again. Then we'd have 2/3. And then same thing, 2 divided by 6 is 1/3, and we already have that one there, so we don't need to do that one again.
Okay.
So then we'd have 5 halves, 5/3, 5/6, and 10. And then 10 divided by 2 is 5, which we already have. 10 divided by 3 we need. And then 10 divided by 6 is 5/3, which we already have. So a much longer list of possible rational roots. Roots means the same thing as zeros. Okay.
Okay.
So we can start with 1. Two's no good. 10, positive 10, 0. Sweet. Okay, so what we know then is p of x can be partially factored into x plus 1 and 6x squared plus 11x minus 10.
Okay.
And then we try to factor this quadratic expression, and if it doesn't, then we can use the quadratic formula.
Okay.
Now, the factor by grouping method, 6 times negative 10, that's negative 60. So we need factors of negative 60 that would add to 11. And if we did 15 and negative 4, so then what we do is we split up that 11x into 15 and 4, so it would be 6x squared plus 15x minus 4x minus 10. And group the first two terms, and from that you can factor out a 3x. And then when you group the next two terms, you can factor out a negative 2. And that leaves you with 2x plus 5 as well. So then the two factors are 3x minus 2 and 2x plus 5, with the addition of that x plus 1 that we had found already. So those are the three factors, because we want to have three factors because we started with a third degree polynomial. So fully factored means 3 factors. Now the fact that we were able to factor everything without using the quadratic formula and without having to use complex numbers, that means each one of these factors is going to give us a real 0. It may pop up in the next problem, we'll have to see, but if we had to use the quadratic formula to find the zeros from that, and if we get non-real zeros that have I in them, what that means is our factors from that wouldn't be X-intercepts because they aren't real numbers. The only X-intercepts we get are from zeros that are real zeros from factors that contain. We list the zeros then, and each one of these have a multiplicity of 1, so none of these bounce either. It's not to say that on the final exam they may or may not, so it's just, again, worth going back and taking a look at some problems where they have a multiplicity where the zeros bounce instead of cross. So we have x equals negative 1, x equals 2/3, and x equals negative 5/2. Those zeros come from, like this one, for example, 2x plus 5. If you set it equal to 0 and solve it, you're going to get subtract 5 and then have to divide by 2 in order to solve that. So that's your 0.
Okay.
The y-intercept we can find like we did in the last problem. If you plug in a 0 for all the x's, and again, you could either do it in the factored form that we have here, or if you go back up to the original polynomial and let all of the x's equal 0, you would just have a negative 10 left over.
Okay.
So the y-intercept is 0, negative 10 rather.
So I got
Problem 1, this is degree 3. So the end behavior, since it has a positive leading coefficient, the right side's going up, left side's going down, just like with the last one. So we have an x-intercept of negative 1, 2/3. Negative 5/2 is negative 2.5, so that's right in between negative 2 and negative 3. And then the y-intercept is way down here at negative 10. And the left side's going down to negative infinity, the right side's going up to positive infinity. There's so little space between all of them, I wouldn't, there's not, I mean, the only one you really could would be right there. There's an integer value between negative 1 and negative 2.5. I'm not going to sweat it too bad for a problem like this where there's not such a big span. So you'd be fine to come up, down. It's got to go all the way down to negative 10, and then it comes back up like that.
all right. Yeah, that's what I got.
It may also be wise to think about domain and range when we're graphing. If it's asked, the domain for something like this, for example, domain would be all real numbers, negative infinity to positive infinity. Range would also be all real numbers, positive infinity to negative infinity.
Yeah.
Now, number 3 is, we may not have seen one like this on one of our chapter exams, but it follows the same idea of what we just did. Pretty much it's the same thing we just did, we're just not going to graph. When it says solve the polynomial equation, what we need to do is put it in factored form. So for this one, number 3, for example, we're going to have 3 factors, and they're all going to be equal to 0. And then once we have the, let's say like we have x minus 1, x plus 2, and x minus 5 as our factors. The solutions are just going to be x equals 1, x equals negative 2, and x equals 5. That's what we're doing here.
All right.
So it follows almost exact same steps as we did in problem 1 and 2. The only thing we're not going to do here is graph. So we still need to find p divided by q to give us a list of possible rational zeros. P is negative 2 there, so the factors of P are plus or minus 1 and plus or minus 2. The factors of Q are plus or minus 1, 2, 3, and 6. So then if we divide each factor of P by each factor of Q, we're going to have 1, 1/2, 2, 2/3, 1/3, 1/6. Well, then we test them using the synthetic division. And I'm getting that 1 works.
Okay.
So we know partially factored is x minus 1, and then 6x squared plus 7x plus 2. And now that we have a quadratic, we can try to factor it, or we can use the quadratic formula if it doesn't factor. 6 times 2, there's 12. So if it factors, we'd need to be able to find factors of 12 that add to 7. 4 and 3 would work.
Yeah.
Now and this is for you two that are listening and for everybody that would hopefully will listen to this. All 3 of the problems we've done so far, 1, 2, and 3, the quadratic that has resulted has factored. It doesn't always work like that. If you remember, sometimes you have to use the quadratic formula. So it is a good idea to go back and review finding zeros using that quadratic formula. You understand what I'm saying?
Mm-hmm.
Okay. But this one's going to factor, so we got 6x squared. The 7x is going to split up into 4 and 3, so 4x plus 3x plus 2. When we group those first 2 terms, we can take out a 2x. That leaves 3x plus 2. When we group these last 2 terms together, the only common factor that 3x and 2 have is positive 1. And since they both have a factor that matches 3x plus 2, that's one of the factors. The other one is 2x plus 1. So the polynomial fully factored on the left side of the equation is x minus 1, 3x plus 2, and 2x plus 1. And that equals 0. And then we solve each factor equal to 0 separately. So x minus 1 equals 0 means that x equals 1. 3x plus 2 equals 0 means that x equals negative 2 thirds. And 2x plus 1 equals 0 means that x equals negative 1/2. And those are the 3 solutions. And like I was saying earlier, these are 3 real solutions because those are all 3 real numbers. One of the theorems we talked about in chapter 3 was that a 3rd degree polynomial has the same number of solutions as the degree. So this will have 3 solutions, but doesn't guarantee that they're all real solutions. If we have had to use the quadratic formula here, it would have been possible to have 2 non-real solutions there containing I.
Okay.
So there's that one. Okay, now they want us to write a polynomial that's degree 3.
Mm-hmm.
So it's going to have 3 factors, and we get factors from the zeros that they've given us right there.
Yeah.
So first thing we would do is say if x equals 1, then x minus 1 is a factor, x minus 2 is a factor, and x plus 4. And then we'll deal with this at the end once we've multiplied these 3 together, the leading coefficient of 2. What we just need to do is multiply by 2 at the end. So we would need to multiply these all together, all 3 of these factors.
Mm-hmm.
And you can do this in any order. I'm going to do the last 2, multiply those two.
Okay.
So x minus 2 multiplied by x plus 4, we're going to have x squared plus 2x minus 8. And then we multiply that by x minus 1. We're going to have x cubed plus 2x squared minus 8x minus x squared minus 2x. Just using the distributive property there to distribute the x and then distribute the negative 1. So combining like terms. And then this leading coefficient of 2.
Yeah.
We would now take, whoops, the whole thing, multiply by 2.
Okay.
And it's important to note that you'd multiply the whole polynomial by 2, not just multiply the leading coefficient by 2. If you just multiply one term by 2, you're changing the whole polynomial. If you multiply every term by 2, you're not changing the zeros of the polynomial.
Okay.
Part B is really similar. It's degree 3, but they've only given us 2 zeros. And it's because of this one right there, x equals 1 plus I. If you remember, those kind of zeros, those non-real zeros or complex zeros, they always come in pairs. So another one is x equals 1 minus I. Complex zeros always have to come in what are called conjugate pairs. And it's typical. If you have a complex zero, they usually leave one off to see if you remember what the rule is there. So now we have 3 zeros.
Okay.
So we do the same thing. We form the factors first. So one of them is going to be x plus 3. That comes from that 0 of x equals negative 3. Now the other two complex zeros, x equals 1 plus I, for example, the safest way to form a factor from that is just move these terms over to the same side as x so you can get it equal to 0. So you're going to have x minus 1 minus I equals 0. So that's one of your factors.
Okay.
X minus 1 minus I. And if you do the same thing with the other 0, so x equals 1 minus I, if you move both of those to the same side as x, you're going to subtract 1, but add I. So it's going to be x minus 1 plus I. And when you're multiplying factors together that contain complex numbers, it's best if you multiply those two together first.
Okay.
So if you multiply those two factors together first, using the distributive property, you're going to distribute x to all the terms. So that's going to give you x squared minus x plus ix. And then you take this negative 1 and distribute it to the other terms. So that's going to be minus x plus 1 minus I. And then you take this negative I and distribute it to all three terms, and you get minus ix plus I minus I squared. And at this point, you know you've done it correctly. I mean the multiplication. You know you've multiplied correctly if any term that has an I cancels. If that doesn't happen, you've made a multiplication mistake somewhere. So any term that has an I should cancel with a term that's opposite from it.
Okay.
Including the I squared equals -1. So you can replace I squared with -1. So minus I squared really turns into minus -1, which is +1. So you just replace that with a +1. So combining all the like terms there gives you x squared minus 2x plus 2. And then you got to multiply that with the x plus 3. You're going to get x cubed minus 2x squared plus 2x plus 3x squared minus 6x plus 6. When you combine all the like terms, you get x cubed plus x squared minus 4x plus 6. This one's a lot. These ones take a little bit of work. Yeah, they just said leave it as 1. If they had said, all right, leading coefficient of 4 or whatever, then at that step you would multiply the whole thing by whatever it said.
Okay.
Okay, we are, this is from section 3.6, both of these problems.
All right.
This is graphing rational functions rather. What I would do first is factor where you can. And pay particular attention, especially for part A and for part D, the domain, particular attention to your denominator. We can't divide by 0, so x cannot equal 3, and x cannot equal 1.
Okay.
And that's where you place, if you remember, that's where you place your vertical asymptotes. Those are the domain restrictions.
Oh, yeah.
So x equals 3. When it says show and label, they just mean give the equation of the asymptote. So x equals 3 is one of your vertical asymptotes, and x equals 1 is the equation for the other one. So that would be what we've done here. We draw the vertical asymptote and we label them. That's sufficient for part A. Part B, show and label the horizontal asymptote. This is where you compare the degree of the numerator and the denominators. And the numerator has a degree 1, the denominator has a degree 2.
Mm-hmm. So it's 1/2.
Well, if they have the same degree, like if that were an x squared, if they have the same degree, then you divide the leading coefficients. If the numerator has a smaller degree than the denominator,
It's
then
zero.
exactly, the horizontal asymptote is 0. So you just got to remember, if the numerator has a smaller degree than the denominator, the horizontal asymptote is y equals 0.
Can you say that one more time?
Yeah. So going back to the original problem here, the numerator is degree 1 and the denominator is degree 2. If the numerator has a smaller degree, then the horizontal asymptote is always 0. If the numerator has a smaller degree than the denominator, then the horizontal asymptote is always 0.
Okay.
So that, just drawing the horizontal asymptote and labeling it, that's sufficient for part B. For part C, we find the X and Y intercept. And this is just like any other function. If we want to find the y-intercept, for example, if we want to find the y-intercept, we let x equal 0.
Mm-hmm.
And you can do that in either the factored form that we created, or you can use the original form. If you let all the x's equal 0 in the original form, for example, then you just have 2/3. So the y-intercept is 0, 2/3. X-intercept of any function, not just rational functions, but x-intercepts are found by letting y equal 0, and f of x is the same thing as y. So if you put a 0 in for y, the only time a fraction is going to equal 0 is when the numerator equals 0. So really, we're just worried about that equation there. The only time a fraction equals 0 is if the numerator equals 0. So x plus 2 equals 0 just means that x equals -2.
Okay.
So that's your x-intercept. Okay, for part D, it says write the domain in interval notation. We had a good start. We knew that x cannot equal 3 and x cannot equal 1, but it can equal everything else. So for part D, the domain, if we think number line, for example, the real number line, if we take off x equals 1 and take off x equals 3, I'm just going to put an open circle there. But then everything else is in the domain. That leaves us with 3 intervals. We have this interval from -infinity to 1, and then we have 1 to 3, and then 3 to infinity. So that would be our domain. Okay, graphing now for part E. These kind of graphs, if you remember, are kind of separated by the vertical asymptote. There may be a piece here, there might be a piece here, and you know, a piece kind of like this. We just got to figure out where the pieces are.
Mm-hmm.
So if we look at the right side, for example, over here, we're either going to have a piece of the graph up in the top right corner, or it's going to be down here in the bottom right corner. Do you remember how it was we determined where?
You just plug a number for x.
Yeah, just pick a random number for x on this side of the vertical asymptote. So if the vertical asymptote is at 3, then choose anything bigger than that, like 4, and plug it in. So if you plug in x equals 4, to this, for example, 4 plus 2 is 6. 4 minus 3 is 1. 4 minus 1 is 3. So 6 divided by 3 is 2. So when you plug in a 2, when you plug in a 4, we got a 2 out of that, 4 comma 2.
Mm-hmm.
What that tells us is that piece of the graph looks like that. Now in the middle between the two vertical asymptotes, oftentimes these graphs, they may look something, they may look something like that, right? Do you remember seeing things like that?
Yeah.
Or it could look like that. The problem is there's not an x-intercept anywhere in the middle. So it's not going to cross through the x-axis. It's either going to be a parabola type shape somewhere like this, or somewhere down here like that. And again, the only way to know is to plug in a point. So I'm going to plug in x equals 2. So we plug in x equals 2, in the numerator we're going to get 2 plus 2, which is 4. 2 minus 3 is negative 1. And 2 minus 1 is 1. 4 divided by negative 1 is negative 4. So when we plug in a 2, we get negative 4. That doesn't necessarily mean that's the vertex, but just for the sake of simplicity, let's just say it kind of looks like that. On the left side, we've got these 2 points here. We've got our 0 of negative 2, and we have our y-intercept of positive 2/3. So what we need to figure out then is what the graph looks like. Now, the graphs always cross through a y-axis. They never bounce off a y-axis. So I know it crosses through right here, and it's going to get closer and closer to this vertical asymptote. And if you remember our discussion, when graphs near a vertical asymptote, they don't just stop. They either go to positive infinity or they turn down and go to negative infinity. But there's no x-intercept right here. So it can't turn down to go to negative infinity. It's got to continue to go up to positive infinity. And as far as what happens at this x-intercept, when it crosses through, it's not going to continue just to go down like that, because the other discussion we had was the purpose of a horizontal asymptote is to give the graph its shape when x approaches negative infinity or positive infinity. So it crosses through, comes back up, and follows that horizontal asymptote out to negative infinity. Very, very weird shaped graph. Okay, we're almost done. One more. I hope. One more? Yeah, one more. So like we did with question 5, first thing we do is consider everything here in factored form. So x squared plus x minus 2, that's going to be x plus 2, x minus 1. All right, now hold on a second. This denominator, first thing we could do is just factor out an x, and that's going to leave you x squared minus x minus 6. And then if you continue to factor that, okay, hold on now, x squared minus x minus 6, that's x minus 3 and x plus 2. Okay, this, so David and Kobe, and then for anybody else that hopefully listens to this later on, this brings up a point that I mentioned very briefly in lesson 3.6. It was not on the exam for chapter 3, and there might have been one homework question relating to this. I mean, it should be part of part B, so I'm going to add something to part B. Or actually part A, sorry. Label the vertical asymptotes, if any, and then also any holes in the graph. If you notice, when we have fully factored form, the x plus 2 factors are going to cross out, right? So when factors cross out in this process, when we're graphing rational functions, let me actually back up. Before crossing it out, if you look at just the denominator, you might say, well, there's 3 different vertical asymptotes, x equals 0, x equals 3, and x equals -2. But there aren't actually 3 vertical asymptotes because the x plus 2 crosses out, right? Anytime a factor crosses out, that creates a hole in the graph. So there is a hole. There is a hole when x equals -2 because it's a factor that was factored out. The factors that remain in the denominator, x and x minus 3, those are going to give us our vertical asymptotes now. So one of them is going to be this one, which is x equals 0. So there's one vertical asymptote. And the other one is going to be x equals 3. So just to be clear, when we fully factored the original problem, we did have 3 factors in the denominator, but this one does not become a vertical asymptote because it factored out with that same factor in the numerator. When you factor out, though, it creates a hole in the graph. So there is a hole at x equals -2. And I'll show you what that means, what that looks like when we graph it. Now the horizontal asymptote, just like we did for question 5, we compare the degrees of the numerator and denominator. Because the numerator again has a smaller degree, then the horizontal asymptote is just 0. If they happen to have the same degree, remember, if they have the same degree, you just divide the leading coefficients, and that would be your horizontal asymptote. Okay.
Hey, I got another class starting, but I'll finish this later.
Yeah, you're good. It'll be recorded. It'll show up later tonight on the recording.
Sweet.
Okay, we'll see, bud. Show and label the X and Y intercepts, if any.
So the vertical asymptote will be 1, right?
Say that again.
The vertical asymptote?
The vertical asymptote?
Yeah, will be 1.
So those vertical asymptotes come from the factors in the denominator.
Oh, yeah. They are horizontal, I mean.
Yeah. Oh, the horizontal? Are you talking the horizontal or the vertical?
Let's see, because you mentioned when we divide the
the coefficients?
Coefficients, yeah.
Yeah, that's only if the numerator has the same degree as the denominator.
Okay, yeah.
So since the numerator is a smaller degree, just like with the problem above it, we say that the horizontal asymptote is 0. Yeah. When you have the same degree, then you divide the coefficients.
Yeah, I missed that part.
No, you're good. Now for part C, the y-intercept, we find by letting x equal 0. The problem is x equals 0 is one of our vertical asymptotes. So x can't equal 0. What that means is there is no y-intercept because we have a vertical asymptote right along the y-axis. So there's no y-intercept. The x-intercept we get by letting y equal 0. Which means we solve this equation. The only time a fraction is going to equal 0 is if the numerator equals 0. So we need to solve 0 equals x plus 2 times x minus 1. So the two solutions for that equation would be x equals negative 2 and x equals positive 1. And this goes back to what I was saying right at the beginning. There's a hole in the graph when x equals negative 2 because of this crossed out factor. So that x-intercept right there of negative 2 comma 0 is actually a hole in the graph. What that means is just an open circle rather than a closed circle. And then x equals 1 is your typical x-intercept. And then to figure out where the pieces all are, we can do the same thing we did with the last problem. On the right side of that vertical asymptote, for example, we can plug in x equals 4. If we plug in x equals 4 here, we're going to get 4 minus 1, which is 3. And then 4 times 4 minus 3, which is 1. So we get 3/4. When we plug in a 4, we get 3/4 for y. So 4 comma 3/4 means we have a piece of the graph up there. Now right here, I'm going to plug in a point when x equals 2, because if it's up here, that means the graph looks like that. If the point is down here, it means the graph looks like that. So I just need to figure out where the graph is when x equals 2. So if you plug in x equals 2 for those, you get 2 minus 1, which is 1. And then 2 times 2 minus 3. So that's negative 1/2. So 2 comma negative 1/2 means that part of the graph looks like that. Now I also need to know where the graph is at negative 1, because if it's up here, then the graph is approaching positive infinity. If negative 1 gives me a point down here, then it's approaching negative infinity. So we need to figure out where the graph is at negative 1. So if we plug in a negative 1, we have negative 1 minus 1 is negative 2, and then negative 1 times negative 1 minus 3 is negative 4. So negative 2 divided by 4 is negative 1/2. I'm also going to plug in negative 3 on the other side of that hole. Negative 3 minus 1 is negative 4. And then negative 3 times negative 3 minus 3, that's negative 6. So negative 4/18, that's still negative. That's what it looks like here. As it just kind of skims along. There's a hole in the graph when x equals negative 2. Just kind of skims along that horizontal asymptote all the way out to negative infinity. And that should do it.
And what's the domain of this?